After studying this module, you shall be able to know about the conditional stability constant, learn about the basics and theory of conditional stability constant, know how to calculate the conditional stability constant, understand the concept by a model reaction, learn the osmosis method, and understand how the questions can be asked related to the conditional stability constant. Conditional stability constants were proposed by G. Schwarzenbach in 1957 for considering acidic and basic phenomena taking place at the same time with complexation phenomenon. The conditional stability constants were first established in the case of concerned titration of tetraanionic EDTA with some metal ions. In 1959, scope of their application was further extended to other parasitic phenomena by A. Ringbaum. At ambient solution conditions, the equilibria for the formation of coordination complex is illustrated by conditional stability constants given by KML. A coordination complex is generally composed of a central metal ion Mn+, which is surrounded by ligands represented L like water, or a ligand such as ethylene diamine tetraacetic acid EDTA. Some ligands, for instance EDTA, can coordinate through multiple donor sites, for example bis, tris, tetra or hexacylation with the central atom. In general, as the coordination number of EDTA increases, the stability of the resulting complex also increases. It is widely used and examined against other polyamino polycarboxylic acid ligands to determine the stability of complexes, particularly with divalent transition metals. The analytical methods like calorimetry, potentiometry, polarography, spectrophotometry and proton NMR have been successfully applied to determine the conditional stability constants for the reaction between different metal ions and ligands. These analytical methods may also be used for the determination of conditional stability constants for a complex. In the potentiometric titration experiments, the acidic solution containing metal ions and the ligands are titrated with hydroxide ions, and the change in pH is monitored during the titration. On the other hand, keeping pH constant and changing the ionic strength can also be monitored. Likewise, numerous such parameters have to be considered before titration of the metal complex. The background informations that need to be obtained are the ligand protonation constants pKa along with the concentration of the metal ions and the free ligands. Conditional constant. Using conditional constants, it becomes easy and fast to quantitatively envisage the course of reactions for complex formation. The fundamental law of the conditional constant concept is based on the analysis wherein the only concentration expected complex is important and not of any other species existing in the reaction. changing the solution conditions, for example, temperature, pH and the ionic strength, the complex formation ability of the ligand is significantly altered, thereby changing the magnitude of the stability constant. Now, let us think about the classical titration of a metal ion Mn plus with EDTA. Now, here we are representing EDTA as H4 EDTA because it has got 4 ionizable hydrogen ions, or Na4 EDTA, in an ammonia-ammonium coupled buffer medium, and maximum number of times it is ammonium hydroxide, ammonium chloride. Imagine that the metal ion also affords amine and hydroxo complexes. Further, let us assume that the investigating complex metal EDTA shows acidic character due to the formation of the complex N-EDTA hydroxide by accepting hydroxide ion, or it may show the basic character by accepting a proton to form a complex shown here as M-EDTA-H, or it may display both the characters. Now, if we assume metal concentration M dash as the total concentration of the metal ion for any ligand species apart from the exact complex in which we desire to connect it along with the protonated or hydroxylated forms of this complex. This is represented as the concentration of metal M dash is equal to M plus MnH3 plus MnH3 whole twice plus metal with the hydroxide ligand plus MOH whole twice, and so on. Further, let us consider EDTA dash as the total concentration of EDTA, that is H4 EDTA and its all anions, apart from the concentration of the complex under investigation. Further, consider EDTA dash as the total concentration of EDTA apart from the concentration of the complex under investigation. So, mathematically it is represented as EDTA dash is equal to the concentration of EDTA 4 negative anion plus HEDTA 3 negative plus H2 EDTA 2 negative plus H3 EDTA negative plus H4 EDTA. Now, note here H4 EDTA is the unprotonated EDTA. Now, consider MEDTA dash as the total concentration of the complex under study. So, this MEDTA dash is equal to the concentration of NEDTA, the concentration of MHEDTA plus the concentration of MOHEDTA. Here M dash concentration, EDTA dash concentration and MEDTA dash concentration are respectively called the apparent concentrations of the metal ion, EDTA and the complex. The apparent concentrations can be expressed as the concentration of metal M dash is equal to alpha M metal concentration, EDTA dash concentration is equal to alpha EDTA, concentration of EDTA 4 negative anion, and the concentration of metal EDTA dash is equal to alpha MEDTA and the concentration of metal EDTA, where the coefficients alpha M, alpha EDTA and alpha MEDTA depend on the experimental conditions and the nature of the species. Considering the stability constants of the various complexes after the expression describing M dash, EDTA dash and MEDTA dash, it is easy to check. For example, here alpha m is equal to 1 plus beta 1 for NH3 plus beta 2 for NH3 square plus beta 1 for hydroxide ion plus beta 2 for hydroxide ion whole square. Here beta 1 for NH3 is equal to the concentration of metal ammonia divided by the product of the concentration of metal M and ammonia NH3. Beta 2 for NH3 is equal to the concentration of metal ammonia 2 divided by the concentration of metal and the concentration of ammonia raised to the power 2. Now here beta 1 for hydroxide is equal to the concentration of MOH divided by the product of the concentration of metal M and hydroxide anion. As well, alpha Y over here is equal to 1 plus beta 1 H plus concentration plus beta 2 for Y H1 concentration whole square. Here Y is EDTA. Similarly, alpha for My complex is equal to 1 plus K of MHY H plus concentration, where beta 1 for NH3, beta 2 for NH3, beta 1 for hydroxide ion, etc. are the overall stability constants for the amine and the hydroxo complexes. It is noteworthy to mention here that the conditional constants have been paid special interest because they can be easily calculated. In fact, the pH of the solution can be known by alpha Y and alpha My, whereas the constants beta 1 and K MHY are determined once for all. However, due to the unknown concentration of free ammonia, the calculation of alpha M seems to be more complicated, as only its analytical concentration is known, which is generally given by this expression: concentration of ammonia CnH3 is equal to concentration of ammonia plus the concentration of metal ammonia complex plus twice of MnH3 whole twice plus so on. Although in presence of large excess of ammonia relative to the metal ion, the concentration of the resulting amine complexes remain insignificant compared to that of the free ammonia concentration. Thus, here we can write the concentration of ammonia is equal to CnH3. For the above experimental conditions, the conditional constant K dash is calculated from the thermodynamic constant K. The thermodynamic constant K expression is K is equal to the concentration of My divided by the product of the concentration of metal M and the concentration of Y. The conditional constants represented as K dash, which governs the concerned equilibrium, is also defined by the expression K dash is equal to the concentration of My dash divided by the product of the concentration of M dash and Y dash respectively. The analyst's main interest in this constant that in fact governs the complex stability as a function of the concentrations of both the ligand and metal ion and independent of their form in the various experimental conditions. Relating the terms K and K dash, we find that it is notable point that relating the terms K and K dash, we find that K is equal to K of alpha My divided by alpha M alpha Y. It is a notable point that in the given experimental conditions, the conditional constants in fact have a constant value. And if the complex formed displays neither acidic or basic character, then alpha My is equal to 1 and K dash is equal to K divided by alpha Y alpha M. Consequently, the thermodynamic constants must be stronger than the conditional constants. That is, K value should be greater than K dash or K dash should be less than K. The ratio for conditional constant and thermodynamic one, K dash by K, can even be very weak. On the other hand, alpha My, which is greater than unity, tends to increase the stability conditional constants value if the complex shows an acidic or basic character. Now, let us study about the calculation of conditional stability constants. Complexes based upon divalent metal ions and EDTA ligand are very strong and within the experimental pH range. As a result, it was considered that each EDTA ligand formed a complex with one metal ion, usually divalent metal ion. The assumption was based on M2 plus by EDTA relationship, which were 1:1 and 2:1 in the standard solution of samples. Two metal-ligand equilibria presented in the sample solution and can be illustrated by the expression given. Here, Kma is equal to the concentration of Lma divided by the product of the concentration of ligand L and metal Ma. Secondly, Kmb is equal to the concentration of Lmb divided by the product of the concentration of ligand L and the metal Mb. Now, the Kma and Kmb are the equilibrium constants for the formation of complex between the two competing metal ions Ma and Mb with ligand L. The concentrations of the complexes have been denoted by Lma and Lmb, whereas L concentration, Ma concentration and Mb concentration are the free concentrations of ligand L and competing metal ion respectively. For competing metal ions, an expression for the stability constant of an unknown complex can be illustrated primarily by combining two equations into another equation followed by developing this expression into equation 4. Here, Kma divided by Kmb is equal to the concentration of Lmb multiplied by Ma concentration divided by the concentration of Lma into the concentration of Mb, which implies that Kmb is equal to Kma, the concentration of Lmb multiplied by the concentration of Ma total, the concentration of Lma divided by the concentration of Lma multiplied by the concentration of Mb total and the concentration of Lmb. Now, the total concentrations of the different metal ions are designated as Ma total and Mb total. The conditional stability constant for metal B, represented as Mb, can be calculated using the above equation provided the stability constant Kma as well as the concentrations of the added metal ions along with both the competing complexes present in the solution are known. Now, it is clear that the value of conditional constant is changed in every reaction at different conditions. The change in beta are less affected by change in the ionic strength. Beta is very much affected in the presence of side reactions. For example, when we react the metal zinc with EDTA, zinc EDTA complex forms and side reactions also takes place, which forms zinc hydroxide, ZnOH, zinc amide, ZnNH2, etc. This is shown over here, zinc combining with EDTA to form zinc EDTA complexes. Interfering metal may be calcium. It can also form side reactions with EDTA, chloride ion, oxide ion, ammonia, etc. Consider a general reaction where the metal M reacts with ligand A to form a complex Ma. Now, here the stability constant Kma is equal to the concentration of the complex Ma divided by the product of the concentration of metal M and the ligand A. Now, in presence of another metal ion, K dash A dash is equal to the concentration of Ma dash divided by the product of the concentration of M dash and A dash. Ringbaum introduced the side reaction coefficient alpha M and alpha A. Now, here alpha M is equal to the concentration of M dash divided by the concentration of metal M. Here M dash is the total uncomplexed metal present in any form and M is the uncomplexed free metal ion. Similarly, alpha A is equal to the ratio of the concentration of A dash to A. Here A dash is the total uncomplexed ligand in any form and A is the uncomplexed free ligand. Therefore, A dash concentration is equal to alpha A, the concentration of A, and M dash concentration is equal to alpha M, concentration of metal M. Now, further putting these values, we get K dash M dash A dash is equal to the concentration of Ma divided by alpha A alpha M. Now, we can take log on the both sides. So, this equation becomes log K dash Ma is equal to log of Kma minus log of alpha A minus log of alpha M. Osmer's method. It is a new method applied for the determination of the composition of weak complexes. It is based upon the equilibria in the form where metal M reacts with n number of ligands A to form MAN complex, and used this method to find the value of n, which may be a fraction value or also an integer number. Therefore, K is equal to the concentration of MAN divided by the concentration of metal into the concentration of A raised to the power n. Taking the reciprocal of the above equation, 1 upon K is equal to the concentration of metal M multiplied by the concentration of A raised to the power n divided by the concentration of MAN. Further, we also know that the concentration of metal M is equal to Tm minus the concentration of MAN. So, taking the reciprocal, 1 upon K is equal to Tm minus MAN whole multiplied by concentration of A raised to the power n divided by MAN. So, this becomes Tm divided by MAN minus 1 multiplied by the concentration of A raised to the power n. If you are taking the concentration of A on the left hand side, so this equation becomes 1 upon the concentration of A raised to the power n is equal to Tm by MAN minus 1 whole multiplied by K value. Suppose 1 upon An is equal to 1 upon Ta to the power n. Therefore, 1 upon Ta to the power n is equal to Tm divided by Man minus 1 whole multiplied by the constant K. Tm minus summation by A minus 1 multiplied by K. Now, if the graph is plotted between 1 upon Ta to the power n versus 1 upon A, the slope is obtained as Tm summation K and the intercept is minus K. Summary: the details about the conditional stability constant and its relation with stability constant and overall constant have been discussed. The various conditions of the reaction that can be changed to investigate the conditional stability constants have been described. The various numerical equations for the calculation of conditional stability constants have been given. Osmosis method and its application toward mononuclear complexes have been illustrated. Several numerical model questions have been provided to get an idea about how to solve the questions based on the given data.